Hello, and welcome back to the Nocturnal Astronomer. I'm your host, Atlas Reid, and tonight we're exploring one of nature's most beautiful phenomena, the Aurora Borealis. Those shimmering curtains of green, pink, and violet light that dance across polar skies have captivated humanity for thousands of years. We'll journey from the surface of the sun to the upper reaches of Earth's atmosphere, uncovering the physics, chemistry, and magnetic forces that create these celestial light shows. We'll discover why auroras appear where they do, what gives them their colors, and how ancient cultures tried to explain these mysterious lights before science revealed their secrets. If you enjoy these types of videos, please give this one a thumbs up and subscribe to the channel. I'd also love to know where you're watching from and what time it is for you right now. Drop a comment below and let me know. Let's dive in. The story of the Aurora Borealis begins 93 million miles away, on the surface of our sun. The sun is not the stable, unchanging sphere it appears to be from Earth. Instead, it's a roiling ball of plasma, hydrogen, and helium so hot that electrons have been stripped from their atoms, creating a sea of charged particles. The temperature at the sun's core reaches around 27 million degrees Fahrenheit, while the visible surface, called the photosphere, sits at a comparatively cool 10,000 degrees. But the real action happens in the sun's outer atmosphere, the corona, where temperatures inexplicably soar to millions of degrees again. This superheated region constantly sheds material into space, a phenomenon we call the solar wind. Every second, the sun releases approximately 1 million tons of matter in all directions, a stream of electrons, protons, and other particles traveling outward at speeds between 200 and 500 miles per second. Think of it like an invisible river flowing from the sun, washing over every planet in our solar system. The solar wind isn't uniform or steady. The sun's magnetic field, generated by the movement of plasma in its interior, twists and tangles in incredibly dynamic ways. Where these magnetic field lines become particularly stressed, they can suddenly snap and reconnect, releasing enormous amounts of energy in events called solar flares and coronal mass ejections. A single coronal mass ejection can hurl billions of tons of plasma into space at speeds up to 2,000 miles per second, carrying with it a powerful magnetic field. These eruptions are like cosmic storms, and when Earth happens to be in their path, the effects can be dramatic. The particles and magnetic fields from these solar events travel across space, taking anywhere from 15 hours to several days to reach our planet. As they approach Earth, they encounter our planet's first line of defense against the harsh environment of space, the magnetosphere. This is where the real magic begins, where solar particles and terrestrial magnetic fields interact to paint the sky with light. Earth is surrounded by an invisible protective bubble called the magnetosphere, a region of space dominated by our planet's magnetic field. This field is generated deep within Earth's core, where a solid iron center is surrounded by a liquid outer core of molten iron and nickel. As Earth rotates, this liquid metal flows and swirls in patterns driven by heat from the planet's interior and by the Coriolis effect, the same force that influences weather patterns on the surface. This motion of electrically conductive fluid generates electric currents, which in turn create our magnetic field, a process called the geodynamo. The magnetosphere extends far into space, reaching out approximately 37,000 miles on the side facing the sun and stretching into a long tail on the night side that extends beyond the orbit of the moon. If you could see magnetic fields, Earth would look like a teardrop or a comet, with a rounded front and a streaming tail pointing away from the sun. This asymmetric shape is caused by the solar wind itself, which pushes against the magnetosphere on the day side and stretches it out on the night side, much like how a strong breeze shapes a flag. The boundary between the solar wind and the magnetosphere is called the magnetopause, and it's anything but stable. As the solar wind presses against this boundary, it creates waves and turbulence, constantly pushing and pulling at Earth's magnetic field. When a particularly strong gust of solar wind arrives, especially one carrying a magnetic field oriented opposite to Earth's, something remarkable happens. The two magnetic fields can merge in a process called magnetic reconnection. Magnetic reconnection is one of the most important processes in space physics. Imagine two garden hoses spraying water at each other. Where the streams meet, the water splashes and redirects. Magnetic reconnection works similarly, but instead of water redirecting, magnetic field lines break and rejoin in new configurations, converting magnetic energy into kinetic energy and heat. This process acts like a gateway, allowing solar wind particles to enter the magnetosphere. These particles get caught up in Earth's magnetic field and are funneled along field lines toward the polar regions, setting the stage for the aurora. Earth's magnetic field lines emerge from the south magnetic pole, arc through space, and converge again at the north magnetic pole, creating a pattern that looks remarkably like the field around a bar magnet. You can visualize this using iron filings on paper held over a magnet. The filings align themselves along invisible lines of magnetic force. Earth's field works the same way, though on a planetary scale, and charged particles from the sun follow these lines like trains on tracks. As solar wind particles enter the magnetosphere through magnetic reconnection, they don't strike Earth randomly. Instead, they spiral along these magnetic field lines, following them as they curve down toward the magnetic poles. This is why auroras appear predominantly in rings around the Arctic and Antarctic regions, in zones typically located between 60 and 70 degrees magnetic latitude. These regions are called the auroral ovals, and they mark the areas where magnetic field lines that extend far into space reconnect with the planet. The auroral ovals aren't fixed circles. They expand and contract, brighten and dim, in response to conditions in the solar wind and magnetosphere. During quiet times, when solar activity is low, the ovals are relatively small and dim, sometimes not even visible without sensitive instruments. But during geomagnetic storms, when a coronal mass ejection slams into Earth's magnetosphere, the ovals can expand dramatically, bringing auroras to latitudes far from the poles. During the most intense storms, people in the northern United States, southern Canada, and even occasionally in the Mediterranean have witnessed the northern lights. The particles channeled along field lines toward Earth don't fall straight down. Instead, they spiral around the field lines in a corkscrew motion, a consequence of the Lorentz force acting on charged particles moving through a magnetic field. As they spiral downward, these particles carry enormous amounts of energy. A typical electron involved in aurora formation might have an energy of 1 to 10,000 electron volts, having been accelerated by electric fields in the magnetosphere. To put that in perspective, these particles are moving at speeds of several thousand miles per second by the time they reach the upper atmosphere. Around 60 to 250 miles above Earth's surface lies the thermosphere, a layer of increasingly thin atmosphere where auroras come to life. Despite its name, which suggests heat, the thermosphere would feel incredibly cold to a human because there are so few molecules to transfer thermal energy. Yet the individual molecules and atoms here have absorbed so much solar radiation that they're vibrating at speeds corresponding to temperatures of 1,000 to 2,000 degrees Fahrenheit. This is the aurora's canvas. When high-energy electrons and protons from the solar wind collide with atoms and molecules in the thermosphere, they transfer their energy through impact. The most common targets are oxygen and nitrogen, which make up the vast majority of Earth's atmosphere. These collisions are like cosmic billiard balls, with speedy particles from space striking atmospheric particles and transferring energy to them. The atoms and molecules that get hit absorb this energy, which excites their electrons to higher energy states. But excited states are inherently unstable. Within fractions of a second to several minutes, depending on the specific atomic transition involved, the excited electrons fall back down to their ground states. When they do, they must release the energy they briefly held, and they do so by emitting photons, particles of light. The color of that light depends on which type of atom or molecule was excited and which energy transition is occurring. It's the same principle behind neon signs, where electricity excites gas atoms to produce colored light, but in the aurora, the energy comes from space. Oxygen atoms produce the aurora's most common colors. When oxygen is excited at altitudes around 60 to 150 miles, it emits a characteristic yellow-green light at a wavelength of 557.7 nanometers. This is the color most people picture when they think of the northern lights, that brilliant green glow. At higher altitudes, above 150 miles, where the atmosphere is thinner and collisions are less frequent, oxygen has more time before it's jostled by another particle. In these conditions, oxygen can emit a deep red light at 630.0 nanometers, though this red aurora is often fainter and harder to see with the naked eye. Nitrogen, the most abundant gas in Earth's atmosphere, contributes the blue and purple hues that often accent auroral displays. When nitrogen molecules are struck by solar particles, they can emit light across several wavelengths. Ionized nitrogen, which has lost an electron in the collision, produces blue light at around 428 nanometers. Neutral nitrogen molecules produce a deeper blue or purple-red color at different wavelengths, adding complexity to the auroral palette. The altitude at which these collisions occur plays a crucial role in determining the aurora's appearance. Lower auroras, occurring below about 75 miles, tend to show more pinks and reds because they involve different nitrogen transitions. The classic green aurora occurs in the sweet spot between 60 and 150 miles, where oxygen is plentiful and conditions are just right for that 557.7 nanometer emission. The rare all-red auroras occur at the highest altitudes, above 150 miles, where the thin atmosphere allows oxygen's slower red emission to dominate. But auroras aren't just about color. They're also about form and motion. The most common form is the arc, a gentle curve of light stretching across the sky like a luminous rainbow. Arcs can remain relatively stable for minutes or even hours, marking the edge of the auroral oval. When solar wind conditions intensify, arcs can transform into bands, which have more structure and begin to fold and ripple like curtains blowing in a breeze. These curtains can develop vertical rays, thin columns of light that shoot upward, aligned with Earth's magnetic field lines. The most dynamic auroras are called coronas, not to be confused with the sun's corona. An auroral corona occurs when the observer is directly beneath the point where field lines converge, making the aurora appear to radiate from a point directly overhead like a celestial crown. Pulsating auroras flicker on and off repeatedly, while flickering auroras change brightness rapidly, sometimes several times per second. These variations are caused by changes in the particle flux and energy arriving from the magnetosphere, which itself is responding to fluctuations in the solar wind. Scientists have measured auroral light intensities and found they can vary by factors of hundreds or even thousands during a strong storm. The brightest auroras can be intense enough to read a newspaper by at midnight, though more commonly they're bright enough to cast faint shadows. The light is cold light, produced by atomic transitions rather than heat, so auroras don't warm the atmosphere below them. They're purely a visual phenomenon, though they're accompanied by complex electrical and magnetic effects that can impact radio communications and electrical systems. Long before scientists understood plasma physics and magnetic fields, cultures around the world crafted explanations for the mysterious lights that occasionally painted their night skies. These interpretations reveal as much about human psychology and culture as they do about observation of natural phenomena. For societies at high latitudes, where auroras were common, the lights became woven into mythology, spirituality, and daily belief systems. Many indigenous peoples of the Arctic developed rich traditions surrounding the aurora. The Inuit of Alaska and Canada had various interpretations depending on the specific group, but many believed the lights were spirits of the dead playing ball games with a walrus skull, while others saw them as torches held by spirits to guide souls to the afterlife. The Sami people of northern Scandinavia treated the lights with respect mixed with caution, believing one should not wave, whistle, or sing at them, lest they come down and carry you away. Children were warned to behave quietly when the lights appeared. In Norse mythology, the aurora had associations with warriors and the afterlife. Some traditions held that the lights were reflections from the shields and armor of the Valkyries, the choosers of the slain who gathered fallen warriors to take them to Valhalla. This interpretation connected the aurora with honor, battle, and the journey after death. Other Norse accounts suggested the lights were a bridge to the realm of the gods, a celestial pathway between worlds, which isn't entirely metaphorical given that auroras do represent a connection between Earth and the Sun. Further south, where auroras appeared rarely and only during major geomagnetic storms, they often inspired fear and were interpreted as omens. Medieval European chronicles describe unusual red auroras visible over Rome, France, and Britain as harbingers of war, plague, or other disasters. In 1738, a particularly intense aurora visible across Europe was documented in numerous accounts, with many interpreting it as a supernatural warning. The red color, caused by high-altitude oxygen emissions during intense storms, was especially unsettling to observers who associated red skies with blood and violence. The scientific study of auroras began in earnest in the 17th and 18th centuries as European natural philosophers started systematically recording observations and seeking natural rather than supernatural explanations. In 1621, French astronomer Pierre Gassendi coined the term Aurora Borealis, combining Aurora, the Roman goddess of dawn, with Borealis, meaning northern, to describe the northern lights. The southern counterpart, Aurora Australis, was named later as exploration of Antarctic regions increased. Edmund Halley, better known for the comet bearing his name, published one of the first scientific papers on auroras in 1716 after a spectacular display was visible over London. Halley correctly proposed that auroras had something to do with Earth's magnetic field, though he couldn't explain the mechanism. He suggested that luminous vapor might somehow be guided by magnetic forces through Earth's atmosphere, an idea that was prescient even if the details were wrong. His work encouraged other scientists to treat auroras as natural phenomena worthy of systematic study rather than as omens or mysteries. In the 19th century, understanding advanced significantly through the work of several key figures. Swedish physicist Anders Celsius and his assistant Olof Heyerdahl discovered in 1747 that compass needles were deflected during auroral displays, providing clear evidence of a connection between auroras and magnetic disturbances. British amateur astronomer Richard Carrington made a crucial observation in 1859 when he witnessed a large solar flare and noticed that a major geomagnetic storm and spectacular aurora followed about 17 hours later. This was the first indication that the sun might be directly responsible for auroras. The Carrington event, as it came to be known, produced auroras visible as far south as the Caribbean and caused widespread disruption to telegraph systems, which were the cutting-edge technology of the era. Telegraph operators reported being able to disconnect their batteries and still send messages using the electrical currents induced in the wires by the geomagnetic storm. Some telegraph pylons threw sparks, and operators received electric shocks. This dramatic event made it clear that auroras were associated with powerful electrical and magnetic forces with practical implications for technology. Norwegian physicist Christian Birkeland made groundbreaking advances in the early 20th century through both observation and experiment. Between 1899 and 1913, he conducted expeditions to northern Norway to study auroras and established observation stations to measure magnetic fields and electrical currents. Birkeland proposed that electrons from the sun were guided by Earth's magnetic field to the polar regions, where they caused atmospheric gases to glow. He even built a laboratory device called a torella, a magnetized sphere in a vacuum chamber, which he bombarded with electrons to create miniature auroras. Today's understanding of auroras rests on decades of spacecraft observations, ground-based measurements, and theoretical advances in plasma physics. The space age transformed aurora science, allowing direct measurement of the solar wind, magnetosphere, and particle interactions that create auroras. Satellites like NASA's Themis mission, the European Space Agency's Cluster mission, and the Van Allen probes have mapped the magnetosphere in detail, while ground-based all-sky cameras and radar systems track auroras continuously from multiple locations around both poles. One of the most important discoveries is that auroras are powered by a complex energy budget involving multiple mechanisms. The solar wind doesn't directly crash into the atmosphere in most cases. Instead, it transfers energy to the magnetosphere through magnetic reconnection, which stores energy in the magnetic field like winding up a spring. This energy can be released suddenly in substorms, which are like miniature internal storms within the magnetosphere lasting 1 to 3 hours. During a substorm, energy stored in the magnetotail, the stretched out part of the magnetosphere on the night side, is suddenly released, accelerating particles down into the atmosphere and creating bright, dynamic auroras. Scientists measure the power input to auroral displays in terms of total energy. A moderate aurora might involve around 10 to the 15th joules of energy, roughly equivalent to the energy of a small earthquake. Major auroral storms during intense geomagnetic events can involve 10 to the 18th joules or more, comparable to a magnitude 7 earthquake. This energy goes into heating the upper atmosphere, creating the light we see, generating electrical currents that flow through the ionosphere and magnetosphere, and producing electromagnetic waves across a wide range of frequencies. Modern research has also revealed that auroras produce sound, though this was controversial for many years. Reports of auroral sounds, described as crackling, whooshing, or clapping noises, were often dismissed as subjective or imaginary because auroras occur far too high in the atmosphere for sound waves to reach the ground from their source. However, recent research has confirmed that auroras can create sounds through a different mechanism. The intense electric fields associated with auroras can cause sparks or discharges from objects on the ground, particularly in areas with temperature inversions that trap a layer of charged particles near the surface. These discharges occur at ear level and create the sounds people report. Despite our substantial knowledge, mysteries remain. Scientists are still working to understand the precise mechanisms that accelerate particles to the energies needed to create auroras, particularly the brightest and most dynamic forms. The role of electromagnetic waves in particle acceleration is an active area of research, with spacecraft detecting a variety of wave types including Whistler mode waves and Alfvén waves that interact with particles in complex ways. Understanding these processes has practical importance because similar physics operates throughout the universe, from other planets' magnetospheres to accretion disks around black holes. Auroras aren't unique to Earth. Spacecraft have observed auroral emissions on Jupiter, Saturn, Uranus, Neptune, and even on some of Jupiter's moons. Jupiter's auroras are particularly powerful, driven not just by the solar wind but also by material ejected from volcanoes on its moon Io, which gets ionized and caught in Jupiter's magnetic field. These planetary auroras provide natural laboratories for testing our understanding of plasma physics under different conditions. They remind us that the interaction between stellar winds and planetary magnetic fields is a fundamental process throughout the cosmos. While auroras are beautiful to watch, the same geomagnetic storms that create spectacular light shows can have significant impacts on modern technology. The relationship between space weather and human systems has become increasingly important as our civilization grows more dependent on satellites, electrical grids, and communication networks. Understanding these effects isn't just academic curiosity, it's become essential for protecting infrastructure worth trillions of dollars and ensuring the safety of systems we rely on daily. The most vulnerable technologies are those that involve long conductors, whether copper wires stretching across continents or the ionized upper atmosphere itself. When a geomagnetic storm occurs, it doesn't just send particles into the atmosphere to create auroras. It also causes rapid changes in Earth's magnetic field at ground level. According to Faraday's law of electromagnetic induction, any change in a magnetic field through a conductor induces an electrical current in that conductor. During a geomagnetic storm, these induced currents, called geomagnetically induced currents, can flow through power transmission lines, pipelines, and railway tracks. Power grids are particularly susceptible to geomagnetically induced currents. Transformers, the devices that step voltage up or down in electrical transmission systems, are designed to handle alternating current at 50 or 60 cycles per second. But geomagnetically induced currents are essentially direct current, flowing in one direction for minutes or hours. When geomagnetically induced currents enter a transformer, they can cause the magnetic core to saturate, meaning it can't properly regulate the alternating current it's supposed to handle. This saturation causes the transformer to overheat, ages its insulation, and in extreme cases can destroy it completely. Large power transformers cost millions of dollars each and can take months or years to replace. The most famous example of aurora-related power disruption occurred in March 1989, when a major geomagnetic storm struck Earth following a solar eruption. The storm caused a complete collapse of the Hydro-Quebec power system in Canada, leaving 6 million people without electricity for 9 hours. The cascade failure began when protective systems detected problems caused by geomagnetically induced currents and shut down transmission lines. As each line failed, the load shifted to remaining lines, overwhelming them in turn until the entire grid collapsed. The storm also caused transformer damage at substations in the United States and Britain, some requiring replacement. Satellites face different but equally serious risks during geomagnetic storms. Spacecraft in low Earth orbit travel through the ionosphere and thermosphere, the same regions where auroras occur. During storms, these layers heat up and expand, increasing atmospheric drag on satellites. This drag can alter orbits, requiring thrusters to fire more frequently to maintain position, consuming precious fuel. In extreme cases, satellites can tumble out of control or re-enter the atmosphere prematurely. In February 2022, a geomagnetic storm destroyed 40 newly launched Starlink satellites worth over $50 million when increased atmospheric drag prevented them from reaching their intended orbits. High-energy particles accelerated during geomagnetic storms pose additional threats to spacecraft electronics. These particles can penetrate satellite shielding and cause single-event upsets, where a particle strike flips a bit in computer memory from 0 to 1 or vice versa. If this happens in a critical system, it can cause software crashes, data corruption, or command errors. More serious are single-event latch-ups, where a particle creates a short circuit that can permanently damage components. Satellite designers include radiation hardening and redundant systems to mitigate these risks, but protection adds weight and cost. Radio communication also suffers during auroral activity. The ionosphere, a layer of the atmosphere ionized by solar radiation, normally reflects certain radio frequencies back to Earth, enabling long-distance communication. But during geomagnetic storms, the ionosphere becomes turbulent and irregular, causing radio signals to scatter, fade, or disappear entirely. High-frequency radio used by aircraft flying over polar regions, by ships at sea, and by military communications can become unreliable or unusable. GPS signals, which must pass through the ionosphere, can experience errors of tens of meters instead of the usual few meters, affecting navigation systems worldwide. Astronauts face health risks during major solar storms. The International Space Station orbits within Earth's magnetosphere, which provides some protection, but astronauts still receive elevated radiation doses during storms. During extravehicular activities, or spacewalks, this risk increases because spacesuits provide less shielding than the station itself. NASA monitors space weather carefully and can delay or cancel spacewalks if dangerous conditions are forecast. Future missions to the Moon or Mars will face greater challenges because those destinations lack Earth's protective magnetic field, requiring careful planning around solar activity cycles. Given the potential impacts of geomagnetic storms on technology and infrastructure, scientists and government agencies have developed space weather forecasting systems analogous to terrestrial weather prediction. The United States National Oceanic and Atmospheric Administration operates the Space Weather Prediction Center, which monitors solar activity and issues warnings of approaching storms. Similar agencies operate in Europe, Japan, China, and other nations. These centers track sunspots, solar flares, and coronal mass ejections, attempting to predict when Earth might be hit and how severe the effects might be. Space weather forecasting relies on a network of spacecraft positioned between the Sun and Earth. The most important is the Deep Space Climate Observatory, which orbits at a special point called L1, about 1 million miles from Earth toward the Sun. At this location, the gravitational pull of Earth and Sun balance, allowing the spacecraft to maintain a fixed position relative to both. The Deep Space Climate Observatory measures the solar wind speed, density, temperature, and magnetic field orientation, providing about 15 to 60 minutes warning before those conditions reach Earth. This advance notice allows power grid operators to take protective measures and satellite controllers to put spacecraft into safe modes. However, space weather forecasting remains far less precise than terrestrial weather prediction. While meteorologists can predict the path of a hurricane days in advance with reasonable accuracy, space weather forecasters often can't say definitively whether a coronal mass ejection will hit Earth until it's only hours away. The difficulty stems partly from limited observations. We monitor the Sun primarily from one vantage point, Earth's orbit, giving us only a narrow view of a three-dimensional Sunday. A coronal mass ejection might look like it's heading toward Earth when it's actually going to miss, or vice versa. Improving forecasts requires better understanding of solar physics and more comprehensive observations. NASA NASA's Parker Solar Probe, launched in 2018, is flying closer to the Sun than any previous spacecraft, eventually reaching within 4 million miles of the solar surface. At these close distances, it measures the solar wind near its source, where it's still being heated and accelerated by processes scientists don't fully understand. The European Space Agency's Solar Orbiter, launched in 2020, takes the first images of the Sun's polar regions, areas we've never seen in detail because Earth's orbit keeps us near the Sun's equator. Future auroral research will benefit from advances in both observation and modeling. Ground-based networks continue to expand, with automated cameras and magnetometers providing real-time monitoring across both polar regions. New radar systems can measure three-dimensional structures in the ionosphere with unprecedented resolution. Citizen science projects invite amateur photographers and aurora enthusiasts to submit observations, creating datasets covering wider areas than professional networks alone could achieve. These observations, combined with satellite measurements, feed into sophisticated computer models that simulate magnetospheric physics. The computational modeling of Earth's magnetosphere and auroral processes represents one of the grand challenges in space physics. The system involves scales from individual electrons spiraling along field lines, measured in miles, to the entire magnetosphere stretching hundreds of thousands of miles into space. The physics includes electromagnetic forces, particle collisions, plasma waves, and fluid dynamics. No single model can capture all relevant processes simultaneously, so researchers use different models for different scales and try to couple them together. Progress in this area requires some of the world's most powerful supercomputers. Looking further ahead, human expansion into the solar system will make aurora science even more practical. Any crewed missions to Mars must account for solar storms and radiation, as Mars lacks a global magnetic field like Earth's. Colonists on the Moon or Mars will need accurate space weather forecasts to know when it's safe to work outside and when to take shelter in radiation-protected areas. These future explorers might witness auroras on Mars, where localized crustal magnetic fields create small-scale versions of Earth's light shows, or see the glow of solar wind particles striking the thin Martian atmosphere directly. The study of auroras connects fundamental physics with practical applications, ancient mythology with modern technology, and Earth-bound observation with the exploration of space. Each new discovery raises new questions. Each answered question reveals deeper mysteries. Why do some auroras pulsate at regular intervals? What determines the exact brightness and color distribution we see? How do electromagnetic waves and particle populations interact in the magnetosphere? These questions keep researchers fascinated and drive ongoing missions and experiments. And on that note, we conclude our journey through the science of the Aurora Borealis. From solar eruptions to magnetic fields, from atomic collisions to cascading curtains of light, we've traced the path of particles across 93 million miles of space to the moment they illuminate our skies with color and motion. Thank you for joining me tonight on the Nocturnal Astronomer. I hope this has given you a deeper appreciation for one of nature's most stunning displays. Until next time, keep looking up.